Our process began by distilling the functional and non-functional requirements from the project brief. We also added several extensions to these requirements regarding new components, accuracy, speed, and user-friendliness improvements. The execution of LTS v2 can be divided into several sequential steps. The process begins by parsing a netlist file. This is used to generate an appropriate circuit with its components. The netlist specifies a simulation type to be run. The circuit's contents are used to select a method of analysis. Analysis begins by initializing circuit components using the DC operating point. Linear analysis uses fixed time steps, whereas nonlinear uses dynamic time steps to optimize efficiency. To output at regular time intervals, nonlinear analysis must use interpolation as an additional step before outputting. The current time is increased appropriately depending on the method of analysis. Jump back to the simulation step if current time is less than simulation time. Otherwise, continue to the end.
These are two aspects of our code to give insight into our implementation of LTS-v2. This demonstration emphasizes modularity and polymorphism that forms the foundation of our code, using the BJT implementation as an example.
All components have a general constructor that takes in 3 arguments. These are then processed internally, dependent on the component. This polymorphism allows the circuit module to treat all components equally without knowing about their internal implementations.
Netlist support for DOP model allows the user to specify extra parameters for nonlinear components. The input module passes these arguments to the appparams method. They are then used to adjust the component's default parameters. This happens after all components have been constructed.
Set nodal voltages is a method implemented by every component. It is used to update the component's values when necessary. Here it is used to update the linearized model parameters of the BJT for the next time point.
The IV and div functions shown here are purely virtual methods of the abstract base class component. These methods permit the construction of the matrices required for the analysis calculations without considering the component types present in the circuit. From the outside, all components interact with the circuit module identically. IV returns the current injected into node by a component. Div uses 2 nodes to return a conductance associated with 2 nodes. If both nodes are the same, then the sum of all conductances connected to the node are returned. Otherwise, the negative conductance between the 2 nodes is returned. This method is detailed in the report and is part of matrix construction by element stamping.
One problem with nonlinear components is that Newton-Raphson tends to diverge if the initial guess is far off the stable solution. This occurs when sources are non-zero values. To remedy this, source stepping is used. This method tries to reduce this difference between initial guesses. This is done by scaling all sources by a factor of alpha. Alpha starts at 1 but is reduced if divergence is detected. Once convergence is found, alpha is increased by appropriate steps until alpha reaches 1 again and all sources are back to their full values. A very similar algorithm is used to dynamically control the size of the time step during the bulk of the simulation. We choose 2 circuits to give a representation of LTS version 2's performance.
For our demonstration, we chose to simulate a circuit with all types of linear components: normal and dependent sources, resistors, energy storing devices, and ideal op-amps. Here we demonstrate them all working together. We can directly take the SPICE file from LTSpice and input it into LTS v2, removing extra commands like backano and lib, and simulate it.
Here we plot the output of a piecewise linear voltage source and the output current of the op-amp. The output voltage of the op-amp and the current through the current controlled voltage source. The voltage at node 3 and the current through the inductor. We chose to look at these voltages and currents to demonstrate a variety of components and computation methods. As is clearly demonstrated by comparison with LTSpice, the results are very accurate.
For our second demonstration, we have used all of our nonlinear components: diodes, BJTs, and MOSFETs. Here we can see a 3-stage device: a push-pull stage, a rectifier stage, and a switch stage. Our circuit also requires a model statement for the MOSFET to achieve the desired switching. Showing the results from LTS-v2, in the first plot, the push-pull stage clearly shows the crossover distortion expected, and about 0.7 volt amplitude difference between the input and the output. The second plot shows that the rectifier signal is completely positive, and the switch turns on when the input is about 0.3 volts, the MOSFET threshold voltage. Comparing to LTSpice, taking for example the final output voltage, N4, and the current out of the PNP BJT emitter, it's clear how accurate LTS v2 is when compared side by side with LTSpice. What can be seen here is the voltage at node 2 and the current through resistor R1. Zooming in, it can be observed that there is a small discrepancy between the results of LTSV2 and LTSpice. This is mainly due to the models used by each software. LTSV2 uses a much simpler model for the BJT in this case than LTSpice. Because of this, a very small difference can be seen between the two. However, this difference is insignificant in most cases.